Have you ever wondered how a simple graph could reveal the hidden health of a machine? The vibration spectrum is that gateway, a window that transforms invisible movement into diagnosable patterns. Today, we'll journey from the basics of the spectrum's construction to mastering the connection between spectral peaks and machine components. Imagine standing beside a humming motor. It vibrates, but what do those vibrations mean? To uncover the story, engineers use vibration analysis, a practice that turns raw movement into actionable data. At the heart of this process lies the spectrum, a plot showing vibration amplitude across frequencies, built through the magic of Fourier transformation. Let's start by demystifying the spectrum. In vibration analysis, sensors record how a machine shakes, but raw-time signals can be chaotic. Through mathematical processing, these signals are translated into frequency domain, creating a spectrum that reveals distinct peaks and patterns. Think of the spectrum as an orchestra. Each frequency is an instrument, and the peaks represent the loudest parts. Low-frequency peaks might indicate imbalance, while higher frequencies can signal misalignment or bearing faults. By reading the spectral lines, we learn what's happening inside the machine without opening it up. How is the spectrum built? First, we collect vibration data, commonly using accelerometers attached to key points on the machine. The time waveform, full of details, is transformed using the FFT. This divides the complex motion into individual frequencies, each reflecting a specific mechanical phenomenon. A clean, editorial graphic will show this process, from noisy signal to sharp peaks on a spectrum display. As we examine the spectrum, every peak has a story. A dominant peak at the running speed often means imbalance. Sidebands and harmonics could hint at gear mesh or bearing issues. Motion graphics can help highlight these, showing a shaft rotating, then linking vibration to a peak at its speed. Let's explore some common examples. If a peak appears at twice the shaft speed, it may indicate misalignment. Peaks at frequencies related to bearing components, calculated from their geometry, suggest early signs of wear. Animated diagrams will clarify how these frequencies are determined, simplifying complex math for trainees. Spectral interpretation isn't just science, it's detective work. By linking peaks to machine parts, engineers quickly diagnose problems. The documentary narrative guides viewers through case studies: a pump with imbalance, a fan with misalignment, a gearbox revealing gear mesh frequencies. Confidence comes with practice. As each spectral feature is explained, the viewer's journey moves from uncertainty to competence. By understanding the spectrum's construction and learning to connect peaks to mechanical issues, maintenance teams are empowered to prevent failures before they occur. By the end of this presentation, you'll not only grasp how spectra are built, but you'll see each peak as evidence, a clue pointing to a specific part of the machine. The language of vibration becomes a tool, ready to be applied in real-world diagnostics. Mastering the spectrum opens the door to smart, predictive maintenance. It's the difference between guessing and knowing. As you become fluent in spectral analysis, you'll transform routine checks into confident diagnoses, ensuring machines run safely, efficiently, and reliably every day.